Well, welcome back. We're on to some fairly exciting stuff now. One of my favorite parts of the course. We've done some groundwork. We learned about voltages and how to represent them as complex numbers. Really paid our dues there. Furthermore, we looked at resistors and capacitors and inductors all in the same footing by generalizing the concept of resistance into an impedance. We had resistors which were resistive, capacitors and inductors were reactive, meaning that when they got driven by a sinusoidal voltage, the current they produced was out of phase by plus or minus 90 degrees. And that allowed us to really generalize Ohm's law. So instead of writing V equals IR, we can write V equals IZ now. And if Z is a resistor, Z is equal to R for our resistor here. And for an inductor, ZL, we had that it was equal to a pure imaginary omega L, J omega L. There's an inductor right here. And now it's trying to escape. It's a Rowley inductor, all right. All right, let's just get it there. And ZC for a capacitor, might as well get one of those out here. Here's a capacitor. We had minus J over omega C, okay? And either way, we're just going to call these each, they're all going to be equal to just some, there you go, inductor, some box Z. And we're going to do all the stuff with circuit analysis that we did with DC circuits, which just relied on the linear relation between voltage and current with this complex impedance now. Now, for example, our favorite circuit from the DC components was the voltage divider. Remember the voltage divider we had, if we recall, we had some input voltage, and we had R1 and R2. I guess I should actually look at what I'm writing. And that led to an output voltage that was equal to R2 over R1 plus R2 V in. Now what did that let us do? That let us obtain an output voltage which was less than the input voltage. And we're going to do the same now with impedances. So we're going to generalize this. We're going to make a generalized voltage divider. And what do we get? We get a voltage divider that depends on what frequency we're at. So it might let all the voltage through at one frequency and nearly none of the voltage through at another frequency. So we're going to have our V in, which is some sine wave now, some source. It might be 0 hertz DC. That's allowed too. Cos of 0 is 1. But now we're going to have a impedance here, Z1, possibly a resistor, possibly a capacitor, possibly an inductor, or some combination of all those things. These don't have to be just one element, right? They can be a combination of inductances. And that's going to be my output, our V out here. And exactly as before, we're going to find that V out over V in, which we're now going to generalize and call the gain, but it's the exact same thing. And it's a frequency dependent function now, is just going to be Z2 over Z1 plus Z2. Exactly the same analysis as we had with the voltage divider. Exactly. So we can plug different things in here. If we chose resistors, for example, we'd have Z2 is equal to R2, Z1 is equal to R1, and we'd recover the exact same thing we had before. But it gets really interesting when we have other components that are frequency dependent. Let's look at a simple example. I'll take this capacitor here, put it to ground, my resistor, and we'll hook up a voltage across these two terminals here. And look at the output here. Let's actually sketch that. Let's sketch what that looks like. So that's going to be, it's going to look like this. I'm going to have my input, my AC input, and that's going to be a resistor. That's my Z1. And my Z2 is going to be a capacitor. Okay. and that's my output. And we're pretty much done already because we have our general formula. Let's actually formalize that. Let's write that all down now. So I'll move my circuit out of the way here, my components. There goes the inductor again. And let's see what we actually find here. So for the case of here, we have Z2 is my capacitor, J over omega C, and Z1 is just simply a resistor, R. Okay, so let's do the analysis. So my gain, my V out over V in, is going to be what? Let's have a look. Well, it's Z2 over Z1 plus Z2. So that's J over omega C divided by R minus J over omega C. Okay? And that's it. But we can simplify it to understand it a bit better. Let's multiply both top and bottom by J omega C over J omega C, multiplying it by 1. And negative J times J, what's that? That's 1. 1 over omega C times omega C is also 1. So in the numerator, we're going to get 1. And on the denominator, we get the 1 again down here, plus, I'll just flip them around the way it's normally written, J R omega C. So we have this quantity R omega C in the denominator. So we have the gain, the V out over V in is equal to 1 over 1 plus J R omega C. Okay, that's it. Let's see if we can understand it now. We've done all the math. We just need to do a bit of the physics and think about the limiting cases. So for very low frequencies, very low, let's just say, in fact, that let's just say that omega goes to 0. Well, G of omega, in this case, is going to go to 1 over 1 plus 0, or 1. V out equals V in. Okay, easy enough. So in this case, we have V out equals V in, and everything gets through. We basically get out what we put in. All right, so how about for very high frequencies? Very high frequencies, it's going to look like, well, let's just say again, we'll formally take omega to infinity, and then we're going to get G of omega is 1 over 1 plus infinity times J, but we'll talk about that J in a second. So that's equal to 1 over infinity is 0. So nothing gets through. And we can actually understand this just by looking at the reactance of this capacitor here. For very low frequencies, it's like a snipped circuit. It has like no, it lets nothing through. So for very low frequencies, our circuit, our voltage divider, kind of looks like this. We have our input, resistor, and then like nothing gets through here. So it's basically just a wire. It's a Thevenin equivalent voltage source, okay? How about for very high frequencies? For very high frequencies, our capacitor looks like a wire now. 1 over omega is the impedance. So as omega goes to infinity, the impedance goes to 0. And we have a circuit that looks like this. We've shorted it. This is our ground here. And that's our output. So basically our output is now shorted together. So no voltage is dropped across this point. And that's how we can understand this, this concept intuitively. By the way, what are we doing? We're passing through any low frequencies. They get passed through. The high frequencies get sent to 0. You can think, by the way, of these getting shorted to 0 across this capacitor. And this is what we call a low-pass filter. Low-pass filter. Passes the low frequencies, it shorts the high frequencies out. And all that gets through is the slow stuff. So if we have a very, very fast signal, or a very fast noise, and a slow signal that we're interested in, on top of this very fast noise, we put it through a low-pass filter, that high frequency stuff gets completely zeroed out, and all we see is that low frequency we're interested in. There's high-pass filters too, and we'll get to study those in the course, in the labs, in the course, in the assignments. So this is a low-pass filter. But let's go a few steps further in understanding this. I think we're going to have to switch pages here. So So we'll understand this a bit further, and we'll continue on. We have our low-pass filter, just to remind ourselves, so it's always there. We had a gain, which was 1 over 1 plus j times this omega RC. Okay? Now notice that we figured out kind of what happens asymptotically to the overall gain. It's 1. When omega goes to 0, it goes to 0 for very high frequencies. But it's complex. It's a complex gain. V out over V in is complex. What does that mean? Well, as we learned with sines, a complex, if we multiply a sine wave with a complex number, the complex number has a magnitude and a phase. The phase just corresponds to a time shift. The magnitude will grow or shrink the function. So that's fine. That's great. What we're going to find with our filter then is it's going to shrink the sine wave that we put in by a given amount, and it's going to shift it in time. So let's understand that in terms of its so-called magnitude and phase. To do that, we can write this in terms of its real and imaginary parts. So let's do the following. This is kind of a standard trick to write it in a nice form. Write a complex number in a nice form. We multiply top and bottom by the complex conjugate of the denominator, and that gives us, what does it give us? Well, on one hand, we're going to have 1 plus this times its complex conjugate, which is real plus imaginary squared, omega RC squared. And then we have the imaginary part here, which is going to give us minus j times this omega RC term again over the same denominator. Okay? So that's the exact same way. We haven't changed anything. We've just written this gain in a slightly different form. And now we can actually extract easily the magnitude and the phase of this gain. So let's look at the magnitude. G of omega, the magnitude of complex number. Remember what that is? That's the real squared plus the imaginary part, all squared. Okay, so if we do this, we get the real part squared, 1 squared over the denominator squared, plus omega RC squared over the denominator squared. We're going to get, let's just write it out, 1 plus omega RC all squared over the denominator squared, 1 plus omega RC squared all squared. Fine. This whole term, this is the denominator is just the numerator squared, so we lose that. And we see that the gain, the magnitude, this is how big or small the sine wave is given by 1 plus, the square root rather, of 1 plus omega RC all squared. Oops, 1 over that. Sorry about that. And this confirms our earlier intuition, so that the gain, the magnitude, goes to 1 at omega equals 0 and 0 as we go to infinity. Now there's no complex numbers involved. Well, how about the phase? The phase is given by the so-called argument, arg, of g of omega, and that's merely the arctangent of the imaginary over the real part of whatever we're talking about. Where did that come from again? Remember, there's this real and imaginary. We have a complex number. This is a quick tangent. We have a complex number we can represent graphically as a real and an imaginary part. And this is the phase, this angle here. And it's just rise over run. That's our slope, our tangent. So tan of the imaginary part over the real part is this angle here. Or rather, the imaginary or the real part is the tan of this angle here. That's where that comes from. Okay, tangent off. So in this case, we're going to have what? Negative omega RC over the denominator. I'll just call that D, because we're going to get rid of it in 2 seconds. Over 1 over the same denominator. And that's why I didn't go through all the work of writing that 1 plus omega RC all squared. So this is equal to negative omega RC, or rather tan of the phase we get is negative omega RC. Or equivalently, the phase is equal to the arctan, negative arctan of omega RC. Arctan of negative x is equal to negative arctan of x. So, look at our limiting cases again. At omega goes to 0, we get what? We get arctan, negative arctan of 0. Well, tan of 0 is 0, so arctan of 0 is 0. So we get no phase. The magnitude is the same and there's no phase shift. In other words, we get the exact thing out that we put in. How about as omega goes to infinity? We get negative arctan, in this case, of infinity. What's arctan of infinity? That's actually a well-defined thing. Remember that tan is like the slope? An infinite slope means pi over 2. So negative arctan of infinity is just minus pi over 2, or 90 degrees. Pi over 2 radians. So, as we go to infinity, we get shifted by 90 degrees, and our amplitude shrinks down to 0. Okay, so that's plus or minus infinity. What do I mean by really what we're talking about is frequency being big or small? So from our form of our equation here, I'll just re-highlight this. The relevant term here is this omega RC. We have 1 plus j omega RC. So the frequency being big or small means that omega RC is much less than 1 or much greater than 1 for big or small. Or omega is much less than 1 over RC. So this RC, like in our RC filter, is again a very important frequency. In fact, we'll call this well, this is 2 pi f, and we'll call this the cutoff frequency. Cutoff frequency. And we'll see why in a second. F cutoff for this filter is equal to 1 over 2 pi r times c. Okay? So we have 1 over 2 pi rc is a cutoff frequency. Before that, before the cutoff frequency, this term is small compared to this 1 here. When this term is very small, so we effectively get V out is equal to V in. When this is large compared to 1, this is the part that dominates, and we're going to get our 90-degree phase shift, and the magnitude is going to shrink to 0. Okay, so this is a very important frequency. What is the magnitude at the cutoff frequency? The magnitude is what is G of omega cutoff? Well, that's when omega RC is equal to 1. So that's equal to 1 over the square root of 1 plus 1 squared, 1 over root 2. So at the cutoff frequency, the gain is 1 over the square root of 2. All right? By the way, important side point here. This is the gain is V out over V in. And that is the gain of the voltage. Remember that power is proportional to V squared. So that's like the gain squared. V out, when V out over V in is equal to 1 over root 2, the power at the cutoff frequency goes to 1/2 of its original power. Right? So that's the cutoff frequency tells us when our power that gets through gets cut in half. Okay. Last thing about this is the phase. What is the phase at the cutoff frequency? So phase of omega cutoff from our formula about the arctan here is equal to the arctan of 1. Slope of 1 is 45 degrees. So this is negative pi over 4, or 45 degrees, negative 45 degrees. So at our cutoff frequency, we see that we have half the power getting through, 1 over root 2 of the voltage getting through, and 45 degree phase. So it goes from 0, It's kind of halfway there at the cutoff, down at 45, and then eventually we'll taper out to 90 degrees. Okay, so let's have a look at this. Let's plot our frequency. We'll go onto the screen here and see what we get. So I'm using PyLab inline here. So that means that, well, it basically means I don't have to write NP in front of everything. Things like pi are defined. So now let's look at our impedances. Z1 was equal to R. Z2 was equal to negative J over omega times C. All right, so let's give it some frequencies. Let's say omega is equal to anywhere between, I don't know, a hertz and 10,000 hertz, and we'll give it like a lot of points. And let's call that the frequencies. Okay. Resistance, let's make it a kilo ohm. Capacitance, let's make it a microfarad. And see what we get. So our frequency response now, G is equal to, just from our formula, Z2 over Z1 plus Z2. I love doing it this way because it's all abstract, right? And better actually plot it. So we'll plot the frequency on the x-axis, and the magnitude, which is abs. I had to think about that for a sec, of G. And that's what we get. Let's go from our 1 to our 10,000. So it's not very instructive, is it? In fact, let's do two things. Let's actually look at the phase as well. I'm doing the non-object-oriented version of Python plotting, by the way. So bear with me for one sec. Okay, so now we have some nice figures. Super not helpful. So this is the problem. When we want to look at a frequency response of something, we often want to know what happens near DC and what happens near the high frequencies. And it's very difficult to visualize that range of frequencies simultaneously. We want to know in detail what happens near DC and at, I don't know, a kilohertz and 100 kilohertz. So in order to do that, we're going to use a semi-log plot. So just to explain what a semi-log plot is, problem, we want near DC and high frequency simultaneously. Power is flickering. We've got a windstorm outside, by the way, right now. We want near DC and high omega simultaneously, but the problem is near DC is like 2 pixels on our plot that we just made, and there's a lot of boring stuff near high frequency. So the solution is to use logarithmic scales. So we're going to use a semi-log plot of frequency. And what I'm going to plot then is I'm going to plot the log of frequency. So 1 hertz, door just blew open, 1 hertz is going to go to 0, log base 10 of 1. 10 hertz is going to go to 1, log base 10 of 10 is, is 1, yes. 100 hertz is going to go to 2, because log base 10 of 100. And in general, 10 to the n hertz is going to go to n, because log base 10 of 10 to the n is equal to n. This is all to say that each decade of frequency, each power of 10 in frequency gets equal weighting. So let's go back onto the screen here, and I'm going to now go semi-log plot. Semi-log x of frequency and semi-log x on the other one, and that will be a logarithmic spacing. We'll do that. Let's see what we get. And we get something a lot nicer, actually. We get, let's put the grid here. Okay, I chose a lot of points. And you know what? while I'm here, actually, I'm going to do a little trick. I had to choose like 10,000 points to make it readable. So I'm going to do what's called a log space instead. That's going to give me equally spaced, logarithmically spaced points here. I'm going to go from 10 to the 0 to 10 to the 5. And I'm only going to probably have to do 1,000 points now. There we go. So it's much faster. And we get everything we need. And this way we can go like over a much wider range. Let's go to 10 to the 6. And we can really see a wide range of values here. Okay, so that's great. That's really nice. And that actually allows us to see this whole region here where the frequencies are passed. And then it cuts off very quickly and it goes to 0. Very good. That's very good. Except there's one last thing we want to do. If you can hear it, please ignore my chickens clucking in the background. Now there's one more thing we want to do here. We want to visualize what happens in this region here near the wide frequencies. Everything is condensed to a pixel here. But we're actually we might be suppressing the 1 megahertz a lot more than the 100 kilohertz. But it's all in 1 pixel the way it's plotted now. So we can do the same kind of trick. We're going to plot logarithmically in the y-axis as well. And we're going to make what's called we're going to plot in what's called decibels. We can use decibels. Now x in decibels is going to be equal to 20 log base 10 of x. So that 0 dB is whatever, what would give me 0 dB here? I need this to be 0. So x would be 1. If x is 1, log of 1 is 0, so that'll give me 0. If x is 10, I'm going kind of backwards here, but if x is 10, I'm going to get 20 dB. If x is 100, I'm going to get 40 dB. What if x, by the way, is 0.01, 10 to the minus 2? Well, I'm just going to get negative 40 decibels. So I can just plug in the values here. And what this is going to do is it's going to give me a nice logarithmic plot on both sides. When I do this, I make what is called, well, what I always call a Bode plot, but a German student last year said I should call it Bode or something. Bode. But I'm not a very good German speaker, so Entschuldigung. Mein Deutsch ist nicht sehr gut. Okay, so Bode plot here is, we're going to go semi-log plot of, keep everything on screen here, of G in decibels. So let's go over to the computer again and plot that. Here's where I actually did it. Instead of plotting just the gain, I'm going to go 20 times log base 10 of the magnitude of the gain. And that is my magnitude there. And I just realized I was plotting the same thing on both axes. So what I should have been doing is plotting the angle, perhaps, to give us 2 bits of information here. There we go. And we'll do it in degrees. Just I speak degrees better than I speak radians. So on the left here, we have a Bode plot of my filter. And we can see that we just get, it's not flat. It looks like it flattens out to 0. But what actually happens is it goes linearly down on this log-log plot. And we have a roll-off. So what happens is it kind of keeps rolling off and gets smaller and smaller. The filter gets better and better as the frequency increases. And on the other plot, we see the phase here at around 45 degrees. That's about, I don't know, between 100 and 200. That is roughly where we start rolling off here, around 200. In fact, we can calculate our cutoff frequency is what? Let's actually have a look. Our cutoff frequency is going to be print 1 over 2 times pi times r times c. That's what we said it was, right? So let's do that. So cutoff is that. And we'll make it an F string so we can just plot it nicely. Hertz. All right. Cutoff is 159 hertz. That's about here. By the way, what is the the decibel version of my cutoff frequency? Let's find out. So in dB, it's 1 over, let's actually just look it up, 20 times log 10 of 1 over the square root of 2. Let's see if I forgot any brackets. Probably. Oh no, that's 3 decibels. 3 dB. So the 3 dB point, this is actually an important point here, on a log-log plot, 3 decibel point, there are 3 decibel point, or negative 3 decimal point technically, it gives our cutoff. That's our cutoff. Okay. The last thing I want to talk about with this is the so-called roll-off frequency. And this basically can be understood as follows. So if we have our frequency, went something like this, g of omega was like 1 over 1 plus RC omega squared. And for large RC omega, this is approximately equal to 1 over R times C times omega, or R omega C. So that in decibels, G is equal to log base 10 of RC omega, don't forget that 20, to the minus 1. All right, that's kind of messy, sorry. And that's equal to, we can just pull out the minus 1 due to the laws of logarithms, 20 times log base 10, that's 20 times log base 10 of R times C times omega. We can further use laws of logs. It's a mouthful. 20 log 10 of RC minus 20 log 10 of omega. Okay? Now this is just some constant. We'll call it B, some constant B. This log of omega, we'll call it big W, is what we're plotting. That's our x-axis. And this is going to be our slope. So we see that in decibels, we have negative 20 times W, when we're plotting in a semi-log fashion, plus B. Just some intercept, whatever R times C is. The point is that it's going to have a slope of 20. And this slope is called the roll-off. Roll-off. And for our frequency, for 1 over, basically, if anything that goes as 1 over omega, means we're going to have a roll-off of minus 20 decibels per decade. Okay? We can have fancier filters. For example, something that looks like this. We have an R, C, another R, another C. It's a very cheap way to make what's called a second order filter. We can do the math. Maybe that'll be, I think you do that in your lab actually. And you find that this goes as 1 over omega squared for very large frequencies. And doing the same math, 20 times 1 over omega, 20 times log 10 of 1 over omega squared is minus 40 of our log of omega. So we'd have a 40 decibel per decade roll-off. How fast it falls off is called the roll-off. So if we go back to the screen here, let's actually see if we can verify this. So at 10 to the 5 hertz, we're at about roughly 55 dB. At 10 to the 4 hertz, a decade earlier, we're at roughly 35 decibels. So that is indeed about negative 20 decibels per decade. And that's our roll-off there. So in summary, there's a lot here. We can make, let's just write down our summary here. So in summary, we can make complex voltage dividers, which leads to what are called frequency filters. We can analyze this by plugging in given impedances, and by plotting it, we can form Bode plot, which is a semi-log plot, semi-log frequency plot versus the gain in decibels, and the phase. Okay, we can look at the magnitude and the phase and see what we get. So that's basically it. One thing I didn't realize I didn't quite do here is actually plot what we'd actually expect by putting a sine wave through this filter. So in the last minute, let's just do that really quickly. Let's just hack it out. So I'm going to write, we have our, what is our frequency again? There's lots of them. So let's say we have something in the middle, 500 hertz wave. F equals 500 hertz. Omega equals 2 times pi times f. And t is going to be equally spaced time points. So let's just say it goes from 0 to to about 100 milliseconds. Let's see what that looks like. Plot t versus sine of w times t. And this is my input That's maybe even too much time. Let's go to 10 milliseconds. Yeah, that's pretty good. 20, we got a deal. So this is my input. That's going to be my input voltage that we're going to send in. And let's look at, let's plot it in milliseconds just so it's clear. That's my time. We'll go from like 0 to 20 milliseconds. So we're actually just seeing what we're interested in. That's what we expect from my input. And all right, great label positioning there, Python. Okay, so let's see what we get when we put in a sine wave. So my output sine wave, V out, is just going to be my gain times V in. So my gain is going to be, again, R divided by, it's going to be 1 divided by 1 plus 1j times R times C times W. And we want to go G times V out. But we got a slight problem here. The slight problem is that we're working with complex numbers. So let's just say our V in is now going to be equal to V naught, which is going to be 1 hertz, we'll make it 1 volt, times E to the J times omega times T. And we'll plot the real part of it, or the imaginary, doesn't really matter. V out is not defined. It's a circular reference. And that's what we have. So we have basically the same thing. It's now a cosine instead of a sine, because I called the real part. If I wanted the sine, I'd just go like this. I take the imaginary part. 6 in one, half a dozen in the other. So V out is now G times V in, so let's plot that too. And that's going to be our output. So this is what we would actually expect. If we put something in here. So we see we have a phase shift. It's lagging a bit behind. It's a smaller amplitude. Let's make it solid. Smaller amplitude because the magnitude of our gain has gone down. And it's lagging a bit behind. We have a negative phase shift and it's going to 0. If we put a slightly higher frequency in, we can see it's even smaller wave and it has more of a phase shift. If we put a lower frequency, it's starting to line up really well. Now let's go to maybe spread it out a bit in time. It's starting to line up really well. We have less and less of a phase shift to the point where as we're getting to like DCs, we're getting to like much below the cutoff frequency, V out is almost equal to V in. Okay, so that is it for complex voltage dividers, frequency filters, and Bode plots. And this Python method, by the way, is a very nice way to visualize things because you can put any kind of crazy impedances in. And note that all I had to do is, I didn't even have to do the math. This is after the math here. I just had to write Z2 divided by Z1 plus Z2. And whatever Zs you have, you can plug that in ahead of time, and you can just plot exactly what you'd expect. All right, so fun stuff. This is a really powerful method, and we can go far with this one. So I'll let you guys play with that a bit more in the quizzes, assignments, and the labs. And I'll see you guys next time.